Hello and welcome to this demonstration of the implementation of the finite element method in a commercial software package. The problem we'll be trying to model today is that of steady state heat transfer through a composite wall, and such composite walls are frequently encountered in cold climates. The chief purpose that they serve is to insulate the house from the harsh conditions outside, because typically they will have far lower, say, a loss of heat compared to just a normal regular brick wall. And the problem is stated to us as given here. The composite wall of a house is composed of a 30 millimeter thick plaster layer on the inside, a 100 millimeter thick layer of fiberglass insulation, and a 20 millimeter plywood layer on the outside. The thermal conductivities of each of these materials is given to us. The inside air is at 20 degrees Celsius with a convection coefficient of 10 watt per meter square Kelvin, and the outside air is at negative 20 degrees Celsius with a convection coefficient of 20 watt per meter square Kelvin. We are asked to find the variation in temperature across the composite wall, and a schematic representation of this problem is also shown here on the right, where we have the three walls of given thicknesses and given thermal conductivities, and we are asked to model this. So I'll be modeling this problem in ANSYS, and while the exact steps that I show will be specific to ANSYS, the overall flow of implementation will be much the same across any other commercial software package as well. And because this is a problem of steady state heat conduction, we'll be using the steady state thermal analysis system. So we just select and drag and drop it here. The first step is to add the materials and their properties, which is done via this engineering tab submenu. The first material that we add is plaster, and with plaster we also include the isotropic thermal conductivity property. Note that by default the value for this is in watt per meter per degree Celsius. We should change it to watt per meter Kelvin and feed the value of 0.20. The second material that we add is fiberglass, and again we include the isotropic thermal conductivity, check consistency of units, and then assign a value of 0.04. The third material to be added is wood. We repeat the same steps, and this has a value of 0.12 watt per meter Kelvin. Once the materials are added, we can close this engineering data tab and move on to the geometry tab. Note that for creating the geometry, we have the option of choosing the analysis type, whether it is a 2D or a 3D problem. Given that the present case is just a one-dimensional heat transfer, modeling it using 2 dimensions would be sufficient. And for modeling the geometry, we have several options. It can be done in ANSYS Discovery or ANSYS Space Claim or ANSYS Design Modeler, depending on the features and complexity of the geometry you are dealing with. For this demonstration case, I'll be using Design Modeler. Note that on the bottom left here, the status of the current task is always displayed, like currently it is starting up Design Modeler, and this is the default window which loads. So now we must make this composite wall geometry in Design Modeler. Note that the thicknesses are specified, but we are not told anything about the height. Not that it matters, because this is a case of one-dimensional heat transfer. So we can just assume some arbitrary height, say twice the maximum dimension. The maximum thickness is 100 mm here, so we can just assume a height of 200 mm. So the first step is to choose the plane on which we want to sketch our geometry. In this case, I'll be choosing the XY plane. We can suitably orient the view. and we note that currently the units of length are in meter, and change it to millimeter. Now on the chosen plane we add a sketch by choosing this new sketch option. Then switch to the sketching tab, choose the option of rectangle, and at first just draw an arbitrary rectangle whose dimensions we can specify later. We go to the dimensions tab. The general dimension is selected by default, and we just specify the dimensions here. The values for these dimensions h1 and v2 can be specified on the left. h1 is 30 mm and v2, as we just discussed, can be 200 mm. Now we draw a sketch of the second wall. It involves the same step: choosing the plane of choice, clicking the new sketch button, switching to the sketching tab, choosing a rectangle, then creating your sketch. Again, I specify the dimension for this, and this has a thickness of 100. And a height of 200. And now we specify the draw the third sketch following the same steps. This third wall has a thickness of 20, and its height appears to have matched well, but we'll still check just in case. It is 200. Okay, but these are just sketches and we cannot model using sketches alone. So what we'll need to do is generate surfaces out of these sketches. The way to do it is we choose the sketch, go to concept, surface from sketches. The base object of the sketch is already selected, so we click apply. The operation that we do is add frozen and generate. Now we see that this first surface has been generated. We repeat this for the other two sketches. Choose the sketch, go to concept, surface from sketches, apply, and add frozen. If at this stage I had chosen the operation of add material, what would have happened is the new wall which is getting generated would simply be added to this pre-existing wall instead of being treated as a separate body. Now we see that it also has a slightly distinct color than the previous one, and we repeat this for the third wall. Apply and add frozen, generate. Now we see that our three surface walls are ready, and we can now close design modeler. In our steady state thermal analysis flow, the next step is the model. We double click and wait for it to open. On the bottom right we can see that ANSYS is starting, ANSYS mechanical. It will take a minute to load up. our geometry is loaded. We first check for units. They are currently in mm and Celsius, so it might be a good idea to change it to meters, and for temperature to Kelvin. Okay, so first we must assign materials to each of these walls. That can be done through the geometry tab here. When we select a surface body on the left here, the same is highlighted in this window. The first material is plaster wall, and so we assign the material as plaster. For the second body, which is highlighted here, we assign the material of fiberglass, and for the third, which is again highlighted, we assign wood. The next step is to check for connections between these distinct bodies, and in connections we see this sub tab of contacts, and we have two contact regions created automatically. The first contact region between the plaster and the fiberglass wall, and the second between the fiberglass and wood. For the current case, the contact type is automatically chosen as bonded, which is the appropriate type, but depending on your problem and the physics that you're trying to model, these options may be different. Bonded is the correct option for the present case, and so we leave it as it is. And next we generate the mesh. So a usual practice is to just generate the default mesh suggested by the software and then improve it. So here we see that we are getting a uniform mesh. However, it appears to be a little coarse, and so we can just insert a sizing option here. So say I can have 2 mm element size, and so my current units are in meter, so I will enter 2e-3, which is 2 mm, and then generate mesh. So we see that we get a pretty uniform and fine enough mesh. Of course, for your actual problem, you will have to check for the mesh quality at various regions of your geometry, but for the purposes of the present demonstration, this mesh appears to be good enough. We will now add the boundary conditions which were given to us. So we have the temperature of the air inside is 20 degrees Celsius, and there is a convection coefficient of 10 watt per meter square Kelvin. So we go to this steady state thermal, insert convection. First we have to choose the geometry on which to apply this convection. We go to this edge selection button here, and then choose the left edge. Click on apply, and then the value for the film coefficient is 10, and that for the temperature is 20 degrees Celsius, which converted to Kelvin is 293.15. There's also the convection conditions specified at this outer wall, which is minus 20 degrees Celsius and 20 watt per meter square Kelvin. So we insert a second convection. Again, choose the appropriate geometry to which it has to be applied, which is this outer wall surface here. Click apply. The film coefficient in this case was 20 watt per meter square Kelvin, and the temperature was minus 20 degrees Celsius, which corresponds to 253.15 Kelvin. So we have specified both convection, and in the solution tab we can insert a temperature distribution to view the final results. Then we right click on the steady state thermal and solve. So our solver has successfully completed the process. Now if we choose this temperature distribution tab, we can see the distribution of temperature which is color coded here. So we have the maximum temperature of 291.8 which is pretty much uniform on this inner wall, and then in this fiberglass we see this transition, and on the outer wall a temperature of 253.82. We can also probe these results at specific locations which might be of interest to us, say at some random node or another node here, or we can also see the domain maximum and domain minimum values. And this concludes the implementation of an example problem in a commercial finite element package. I hope you had a good learning experience, and all the best with your course projects. Thank you.